It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee. Okay, welcome to the fourth video for the monitoring the environment topic. This is subtopic 1.4, which is chromatography. Chromatography is a great topic because it's obviously to do with a lot of colors, so this is the reason I've chosen this background image. I think it looks really cool. But chromatography is anytime you're doing it, you can get some really beautiful separation and bands of colors, particularly when you're doing column chromatography. So yeah, it's quite enjoyable. If you don't quite know about chromatography principles, there is actually a YouTube video which is just hiding here underneath me. So this video here will help you go through a few more of the chromatography principles, and I recommend that you click on that if you want. But very quickly, in a nutshell, chromatography involves the use of both the stationary phase and the mobile phase. We use it to separate, isolate, purify, and identify different components in a mixture. So what it firstly does is components have different polarities within a mixture. So what we do is we mix it up within a mobile phase and we pass that over the top of the stationary phase. Now the stationary phase, as suggested, is something that doesn't move, but the mobile phase is something that moves over the top of it. Now, because we've got the different polarities of those components, they will be attracted to the stationary phase, which has a polarity as well, at different rates. Okay? The more strongly it's attracted to the stationary phase, the slower it moves, and we use this term adsorption, which is onto the surface, to determine about how well it is attracted to the stationary phase. So the components separate because they have differences in polarities. All right, if we get a good enough separation, we can isolate them, so get them on their own, and that means we can purify them there and identify what they are based on how long they took to come through or travel over the stationary phase. So here's an example. All right, we've got our stationary phase down the bottom here, and we've got our mobile phase, which is heading in this direction. All right, we've got our components here, which are initially in a mixture. The green ones here are traveling really slowly because they're really strongly adsorbed to the surface of the stationary phase, whereas the red components up here are really strongly attracted to the mobile phase, so they've got very similar polarity, okay, and so they're moving quickly. Now, general rule is polar likes polar or like attracts like. Don't ever use that in an answer because it's a really, I guess, inappropriate way of talking about the attraction or everything within chromatography. But it's a very simple thing to remember: like attracts like. So a polar stationary phase strongly adsorbs polar components. If it's a non-polar mobile phase, that will strongly attract non-polar components. How strongly it's attracted or adsorbed is called the retention factor, the RF. So if we've got paper chromatography or column chromatography, which I'll talk about in a minute, all right, we look at how fast the mobile phases move or how far the mobile phase has moved over a certain period of time, and then how far the component moves. Now, the mobile phase will always move further, which means that you're going to have a smaller number here divided by a bigger number. So that means you're always going to get a value which is less than 1. Okay, if you ever do a calculation for an RF value and you get a value that's bigger than 1, you've got it the wrong way. All right. So thin layer chromatography is very, very simple. The most simplest form of chromatography you can have. It's also known as TLC. Okay, it normally uses chalk, so calcium carbonate, aluminium oxide, or silicon gel as the stationary phase, and these are generally polar. So what you have is a plate, all right, or a chromatogram, like we've got here. And what we do is we draw a line onto here, which is where we're going to spot our samples. Okay, so generally what we do is we spot our samples onto a line, and then we put this in a solution, which initially is below the line, which is our mobile phase. And that liquid travels up our stationary phase here, and this is the solvent front up the top. So this is how far our solvent or our mobile phase has moved in the time we've allowed our chromatogram to evolve. You can see the component A here has traveled further, so that's more strongly attracted to the mobile phase, whereas B and our unknown have moved slower, so they're more strongly adsorbed to the surface of the stationary phase. Okay, so we could say that this one is more non-polar, right, and this one is more polar because we're using a stationary phase that is polar. What we can use, as I said, is we can identify components based on their retention factor. It's pretty easy to see here that B and our unknown have the same retention factor. They've moved the same distance under the same conditions, so they're the same component. Column chromatography takes it to a bit of the next level. So what we do is have a long column or cylinder, which we have a slurry poured into. We normally use aluminium oxide, which again is polar. So you mix it up. Aluminium oxide is like chalk, sort of very chalky sort of material. So you mix it up in liquid and you have it inside your column. And you've got to always keep the solvent level above the level of the aluminium oxide, otherwise it dries out. And so you have your sample that you pour over the top of it. And what happens is that as it moves down, the different components within your mixture are attracted to the aluminium oxide at different rates. So you can see here that the yellow component is very weakly adsorbed to the surface and strongly attracted to the mobile phase, so it moves very quickly. The red one less so, and then the blue one is most strongly adsorbed to the surface of the stationary phase, so it moves slowly. Column chromatography is great if you've got a mixture of components and you want to separate them. When I was doing this in university, I had one that I think had about 7 or 8 different color bands through there because I was dealing with a lot of different metal complexes which had manganese in it and other metals as well. So got all these nice different colors as they were separating out. Gas chromatography, similar sort of process again. We have a column, all right, which is this long tube. Now it's wound around itself like this, okay? All that does is increases the surface area. So what that means is that increases the time that it's within the column, okay? That allows for greater separation. The longer your column, the better the separation you can have. And so in this case, what we're using is a mobile phase, which is a gas, all right, and that passes over the top of a stationary phase. Now there's high performance liquid chromatography, there's gas chromatography. So the name tells you what the stationary phase is. So in high performance liquid chromatography, the stationary phase is liquid. In gas chromatography, obviously the mobile phase is gas. So there's different forms. Okay, and depending upon what you wanted to separate would depend upon which form, which type of chromatography you use. But we're just going to look at gas chromatography here. Okay, and this is a little bit different this time because now instead of looking at the retention factor, because all of our components are going to come out, okay, we look at what's called the retention time. Okay, so if our mixture comes through here and it's very weakly adsorbed to the stationary phase, it's going to travel through the column really, really quickly, and it's going to come out quickly as well. So it's going to have a short retention time. If, however, on the other hand, is strongly adsorbed to the surface of the column, it's going to take a long time to come out and will have a higher retention time. So we can look at a graph similar to this. All right, so here's a mixture of different organic substances that we had. So pentane, hexane, heptane, octane, nonane, and decane. So we're going from 5 carbon atoms long to 10 carbon atoms long. And what's happening here is that the pentane has traveled through really quickly. It's got the shortest retention time here. Okay, so that's the one that traveled the fastest. Fastest, if I can spell, sorry. It's getting late. So that traveled the fastest. So that was the most attracted to the mobile phase. Whereas decane, on the other hand, okay, was the one that was most adsorbed to the stationary phase and traveled the slowest, had the longest retention time. Now you notice that the peaks are different height here as well. And so this is one of the good things about using gas chromatography is that the area under the peaks also tells us the composition. So not only can we work out what's in a mixture, but we can also work out how much of it there is. So clearly you can see there's much more hexane in there than there is nonane, for example, because the area under the peak is bigger. Now, new in this new syllabus is the concept of ion chromatography. Okay, so in the previous ones we've been looking at, gas chromatography, column chromatography, we've basically been dealing with just neutrally charged species. So it could be molecules or whatever, but they've got no charge. Ion chromatography relies upon having a charged stationary phase and having charged molecules that are therefore attracted to it. Okay, so rather than just having like something that's got a slight partial positive or negative charge, so it's slightly polar or non-polar, this is now relying upon full ionic charge. So it also relies upon having an equilibrium, so a system that reaction can go backwards and forwards, and that's important for recharging the actual ion chromatography column that you're using, or the resin. So what we have is an ion exchange resin, all right, as the stationary phase. So that's basically a solid which has ions on top of it. Now they can be either cations or anions. Okay. So ions in the mobile phase are either attracted to the resin if they're oppositely charged in this case. So before, when we had polar molecules attracting to polar stationary phases, if now we have a positively charged stationary phase, that's going to attract negatively charged ions. Okay, so it's kind of a bit the opposite, so it's a little bit different. The stronger the charge of the ion, the stronger it's attracted to or repulsed by the resin. So the relative strength of it, of the ion, is important here as well. So the more it's repulsed, the faster it will move through the column. All right, so just got an example here of what we're using here is a chromatography column here, which has got a resin here, which has got positively charged. So it's a cation exchange column here in a sense. Sorry, this is an anion exchange column, all right, which has got a positively charged surface here. So we're looking at exchanging anions on the surface, okay, of a positively charged resin. Okay, so I've tried to color code things here to make it a little bit more easy. So here we've got a resin which is positively charged. So these positive charges, they stay on the surface of the resin. What we've got here, and I'll show it a bit more clearly on the next slide, is we normally have negative ions on the surface of that resin, and as our mixture comes through, the negative ions or the anions in that solution will displace the negative ions on the surface and come out. Okay, but I'll explain that a bit more on the next slide. But basically what you can have a look at here is that these ones here, these negative ions, those anions, they have less charge density than these dark blue ones. So they're traveling faster through the column because they're not as strongly attracted to the positive cations on the surface. Obviously, any positive cations we've got in our mixture will pass straight through because they're getting repulsed by the positive charge on the surface of the column as well. So what you can see here, we've got our resin, we've got some negative charges on the surface of it. So this is why it's called an anion exchange column, this one, because we've got anions on the surface. This is from our mixture. Okay, this is one of our samples that we're looking at. That comes in and attracts itself to the positive charge, the cation charge at the surface of our resin, and displaces up here the negative charge on the surface. Then what happens is that negative anion from our mixture slowly works its way down the column and displaces other anions at the surface, and then they get replenished from one. So this one here obviously comes back in and replaces itself there. We have an equilibrium set up between the ions on the surface of the resin and those in the liquid phase, and we get to a point where if they're strongly enough attracted to the surface, they won't actually come out of the column. And so what we need to do is then replenish it and flush out anything that's left over. So we do that by using the equilibrium reaction that's set up. So what we've got here, here's the positive surface of our resin that we had, and it's still got some negative anions on the surface of it. Okay, so what we want to do is get rid of those by replenishing it with the chlorine ions that were originally on the surface. So we saturate it, we put in a high amount of chlorine into the mixture, according to Le Chatelier's principle, which is covered in the next topic. You might want to have a look at later on for that, but I'll explain it briefly. According to Le Chatelier's principle, the equilibrium wants to shift to decrease the concentration of this chlorine solution, okay, if we saturate it. And so it does that by forming the chlorine onto the surface of the resin and getting our negative anions, which are part of our mixture, out the other end so we can collect them. All right, so that's kind of the way that ion chromatography allows us to separate charged substances. They're really good with amino acids, for example, in particular. And I suggest if you want more help with this, you check out the YouTube video link, which is here underneath my video, underneath my face, I should say. And that goes into a bit more depth and shows what we're looking at as well. All right, so that's the end of the chromatography one. There's one more video after this, which will be on atomic absorption, atomic spectroscopy, particularly looking at atomic absorption spectroscopy. So as always, if you've got any questions, just ask, but I suggest you have a look at the videos as well that are linked within the actual PowerPoint itself. Thanks, guys.